A vector field is a function that associates a vector to every point in space. Here we refer to physical three-dimensional space, represented by the Cartesian coordinates x, y, and z. Magnetic fields, herein produced by two wires carrying currents in opposite direction, is a prime example of a vector field. For a continuous vector field, we can also define its curl. The curl is given by the del operator cross the vector field V. The curl of a vector field at a given point measures the tendency of field to rotate and its axis of rotation. The explicit expression for the curl is written as shown. You can see that each curl component is given by the cross gradient with the other vector field components. Clearly, this is a vector field, which we will call it the curl field for short in this video. The purpose of this video is to explain why the divergence of the curl field is zero, and what this means physically and intuitively. We begin with the intuitive explanation with illustrations. Let's consider a vector field V in 2D, herein on the xy plane. We see regions where the vector field rotates and regions where it flows in streamlined fashion. For better visualization, let us color code the vectors to denote their sense of rotations, blue for clockwise and red for anti-clockwise. Regions with streamlined flow are denoted in green, as shown. We can quantify the amount of rotation by calculating the curl of the vector field, herein denoted as C. The curl vector points in plus or minus z direction since the rotations of the vector field is in xy plane. The convention is given by the so-called right thumb rule. We illustrate the local curl field in the region where the vector field V has clockwise rotations. Here the curl vectors are all pointing in the minus z's direction. As we transition to the region with opposite circulation, we see that the local curl vectors are flipping directions. As we enter the region with anti-clockwise rotation, the local curl vectors now completely flip sign, pointing in the positive z direction. On the other hand, regions where the flow is streamlined has zero curl as illustrated. We can define the total curl by integrating only the normal component of C over this square region S. The result is a number, commonly called the flux of C through region S. However, since the local curl is defined by small circular loops, it is obvious to see that contributions coming from the overlapping part of the loop with the neighboring loops are perfectly cancelled. Thus, the net circulation comes only from the curl loops at the boundary of the square surface. This can be mathematically described by the line integral of the vector field V along the circumference of the enclosed area as shown. This equality is the well-known Stokes theorem. Simply state, the line integral of a vector field over a loop L is equal to its curl through the corresponding enclosed surface S. Now let's take this argument a dimension higher, to a 3D sphere. Let's consider a local region of the sphere surface and depict its local curl fields. Here the vector fields V are circulating counterclockwise, thus the curl vectors are pointing outwards. On the other hand, for vector fields V with clockwise circulations, the curl fields will instead point inwards of the sphere. In similar fashion, we can compute the net curl by integrating the normal component of C over the surface of the sphere, thus obtaining the flux of C. The flux is positive if the curl field has a net divergence out of the sphere, and negative if otherwise. Recall the Stokes theorem, which says that the surface integral of the curl field over S can be alternatively be computed through the line integral of the vector field V over L. Here L is the circumferential loop that encloses S, but since S is the surface of a sphere, L is non-existent. Thus, Stokes' theorem will enforce these integrals to be exactly zero. We are almost there. To get to the final result, we need to invoke another identity, that the flux through the surface is equal to the volume integral of the divergence over the volume enclosed by the surface. This identity is known as the Gauss theorem We see that this argument holds for any enclosed volume omega. Thus, this result would require that the divergence of the curl field is 0 everywhere. We thus arrived at the result we are seeking, that the divergence of the curl of a vector field must be 0. This result has important implications in many fields of physics. When the curl is divergentless, it implies that the circulation within a closed surface is conserved. This is analogous to the conservation of angular momentum in rotational motion. When making connection to electromagnetism, this reminds us of the Gauss law for electromagnetism, which states that there is no magnetic monopoles. Drawing the analogy here, it implies that a natural way of writing the magnetic field B would be as a curl of a vector field. In electromagnetism, the vector field A is known as the magnetic vector potential. Such a redefinition then ensures that the magnetic field will always be divergentless. Please check out these videos on the Gauss and Stokes theorems if you need a refresher on these topics. You can find them in the electromagnetism playlist. We shall end our discussion with a straightforward mathematical proof of the result. We begin with the definition of the curl of a vector field, given by the del operator cross the vector field V. Written explicitly, each curl component is given by the cross gradient with the other vector field components. Next, we take the divergence of this curl field, which is simply the dot product of the del operator with the curl vector. The dot product of two vectors yield a scalar number. We color code the terms for each vector components for your convenience. We see that terms involving partial derivatives of Vz cancels. So does the terms that involve partial derivatives of Vy, and similarly for the Vx terms. Thus, the divergence of the curl field is exactly 0. Mathematically, this is a very straightforward result and probably deceptively simple. However, the physical meanings and implications of this result cannot be overstated, as elaborated in the previous chapters. I hope this video provides you the physical intuition to understanding why the curl field must be divergentless.